Every star you have ever seen belongs to a single structure. The faint points scattered across the night sky and the sun itself are part of the same vast system. Everything you see above you is moving together through space. That system is called the Milky Way. It does not have sharp edges or a fixed outline. It is a long-lived pattern of motion shaped by gravity over billions of years. We live inside this structure rather than observing it from the outside. Because of this, we see the galaxy edge on instead of as a complete image. Our position turns a vast disk into a soft band of light across the sky. The darker lanes within this glowing band are not empty space. They are regions filled with interstellar dust that blocks and scatters starlight. Behind them, gas slowly gathers, and new stars can eventually form. Long before telescopes, people noticed this same pale band in the sky. Different cultures gave it different stories and meanings. The observation came first. Understanding followed much later. Today, astronomy shows that the Milky Way is a rotating disk with spiral structure. Its form is not static. It changes slowly, guided by gravity, motion, and time. Modern astronomy has revealed that the Milky Way is a spiral galaxy. Its stars are arranged in a broad, rotating disk with curved arms that wind outward from the center. This structure is not rigid, like a wheel with fixed spokes. Instead, it is shaped by gravity and motion acting together over immense spans of time. The spiral form is a consequence of how matter responds to rotation on a galactic scale. The disk of the Milky Way is much wider than it is thick. Most of its stars, along with nearly all of its gas and dust, are confined to this flattened region. When viewed from far above or below, the disk would appear luminous and structured, traced by spiral patterns. Our own solar system lies within this disk, embedded among billions of other stars following similar paths. At the center of the galaxy sits a dense region known as the galactic bulge. Here, stars are packed more closely together than in the outer disk. Many of these stars are older, having formed earlier in the galaxy's history. The bulge appears thicker and brighter because of this high concentration of starlight. Running through the central bulge is an elongated structure called a bar. Evidence from stellar motions suggests that the Milky Way is a barred spiral galaxy. This bar influences how stars and gas move near the center, guiding material inward and outward along its length. Similar bars are seen in many spiral galaxies across the universe. Beyond the disk and bulge lies the galactic halo. This is a vast, faint region that extends far beyond the visible stars of the disk. The halo contains sparse stars, ancient star clusters, and a large amount of dark matter. Its structure is more diffuse and less orderly than the rotating disk below it. Dark matter is an essential part of the Milky Way, even though it cannot be seen directly. Astronomers infer its presence from the way stars and gas move through the galaxy. Without it, the outer regions would not orbit the way we observe. Its invisible mass provides the scaffolding that holds the galaxy together. The Milky Way contains an enormous number of stars, likely on the order of hundreds of billions. Many of them are smaller and dimmer than the Sun, making them difficult to detect individually. What we see in the night sky represents only a fraction of the galaxy's true population. Most stars shine quietly, unnoticed from Earth. Stars in the Milky Way are not spread evenly. They tend to cluster along spiral arms where gas is more concentrated. These arms act as regions where star formation is more likely to occur. Over time, stars drift away from the arms, even as the spiral pattern itself persists. Spiral arms are not permanent groups of the same stars. Instead, they are patterns of higher density that move through the disk. As stars orbit the galactic center, they pass in and out of these regions. The arms remain, even though their individual stars change. Our solar system is located in a smaller structure between two major spiral arms. This region is often called the Orion Spur. It is less dense than the main arms, but still rich in stars and nebulae. From here, we have a relatively clear view of both the galaxy's inner and outer regions. The Sun travels around the center of the Milky Way along with nearby stars. This orbit is slow and steady, taking hundreds of millions of years to complete a single circuit. Over its lifetime, the Sun has made many such journeys. Each orbit carries it through slightly different galactic environments. The motion of stars in the disk follows a general rotational pattern. Closer in, orbital speeds rise quickly. Farther out, they stay surprisingly high instead of dropping the way visible matter alone would suggest. This behavior reveals how mass is distributed throughout the galaxy. It was through studying these motions that astronomers first recognized the need for dark matter. Between the stars lies the interstellar medium, a mixture of gas and dust spread thinly across space. Though it may seem empty, this material plays a vital role in the galaxy's life cycle. It is the raw material from which new stars and planets form. Over time, it is shaped by gravity, radiation, and stellar explosions. Interstellar gas exists in several forms, depending on its temperature and density. Some regions are cold and dense, while others are warm or even extremely hot. These different phases coexist and interact. Together they create a dynamic environment within the galactic disk. Among the most important structures in the interstellar medium are molecular clouds. These cold, dense regions allow atoms to bind together into molecules. Under the right conditions, gravity causes parts of these clouds to collapse. When that happens, new stars are born, quietly igniting within the darkness. Dust grains mixed into these clouds absorb and scatter light. This makes star-forming regions difficult to observe in visible wavelengths. Infrared and radio observations, however, can pass through the dust. Using these tools, astronomers can study stellar nurseries hidden from ordinary sight. Star formation in the Milky Way is not constant everywhere. It tends to occur more often in spiral arms and dense regions. Over long periods, the locations of active star formation shift. The galaxy slowly rearranges where its newest stars appear. The Milky Way contains stars of many different ages. Some formed relatively recently, while others have existed since the galaxy's early days. By studying their properties, astronomers can piece together a timeline of galactic evolution. Each generation of stars leaves subtle clues behind. Older stars are more commonly found in the halo and the central bulge. These stars formed when the galaxy was younger and less enriched with heavy elements. Their chemical compositions reflect the simpler universe in which they were born. They serve as living records of the Milky Way's past. Younger stars are typically found in the disk, especially near spiral arms. They formed from gas that had been enriched by earlier generations of stars. This gradual buildup of elements made more complex chemistry possible. It also set the stage for the formation of rocky planets. Elements heavier than hydrogen and helium are forged inside stars. When stars age or explode, these elements are released into space. Over time, they mix into the interstellar medium. Each new generation of stars contains more of these materials than the last. This slow recycling process links stars across billions of years. The atoms in planets, oceans, and living things were once part of older stars. In this way, the Milky Way is not just a collection of objects, but a continuous chain of transformation. Matter moves, changes, and returns again and again. Some of the oldest visible structures in the Milky Way are globular clusters. These are dense, spherical groups of stars that orbit far from the galactic disk. Each cluster can contain hundreds of thousands of stars packed into a relatively small volume. Their stars are generally old, suggesting that these clusters formed early in the galaxy's history, before the disk took its present shape. Globular clusters move through the galactic halo along elongated paths. Their orbits are tilted at many angles relative to the disk, unlike the orderly rotation of disk stars. This difference in motion hints that the halo and disk formed through different processes. By tracking these orbits, astronomers gain insight into how the Milky Way assembled itself over time. Not all stars in the halo formed within the Milky Way. Evidence suggests that some arrived later, carried in by smaller galaxies that merged with it. These past mergers left behind streams of stars that still move together through space. Though spread out today, they preserve the memory of their shared origin. One of the clearest examples of this process involves a small companion known as the Sagittarius dwarf galaxy. This galaxy is currently being pulled apart by the Milky Way's gravity. As it stretches and dissolves, its stars form long, looping streams that wrap around our galaxy. These streams act like fossil traces of an ongoing interaction. Such mergers are not violent collisions between individual stars. The distances between stars are so large that direct impacts are extremely rare. Instead, the interaction unfolds through gravity acting on entire systems. Over hundreds of millions of years, shapes change and material is redistributed. The Milky Way's central region is among its most complex environments. Near the center, stars are packed tightly together and gas clouds move under strong gravitational forces. Conditions there are very different from those near the Sun. Understanding this region helps reveal how galaxies behave under extreme density. At the very heart of the galaxy lies a compact source known as Sagittarius A. Careful measurements of stellar orbits near this point show that an enormous mass is confined to a very small region. The most consistent explanation is a supermassive black hole. Its mass is inferred, not seen, through its gravitational effects. This central black hole is relatively quiet compared to those in some other galaxies. It does not currently consume large amounts of gas or emit intense radiation. Even so, its gravity dominates the inner few light years of the galaxy. Stars there move rapidly along tight, curved paths. Surrounding the central black hole is a dense nuclear star cluster. This region contains stars of different ages, including some that appear surprisingly young. Their presence suggests that star formation can occur even in such extreme environments. The exact processes involved are still being studied. Dust obscures much of the galactic center when viewed in visible light. As a result, early observations struggled to reveal its true nature. Infrared and radio wavelengths can penetrate this dust more effectively. Using these tools, astronomers have gradually uncovered the hidden core of the Milky Way. The Milky Way emits light across the entire electromagnetic spectrum. Radio waves trace cold gas and magnetic fields. Infrared light reveals warm dust and star-forming regions. X-rays and gamma rays point to energetic processes like supernova remnants and particle acceleration. Magnetic fields thread through the galaxy on large scales. Though weak compared to everyday magnetic fields on Earth, they influence the motion of charged particles. These fields help shape interstellar clouds and affect how cosmic rays travel. Their full structure is complex and still not completely mapped. Cosmic rays are high-energy particles that move through the Milky Way at nearly the speed of light. Many originate from shock waves produced by supernova explosions. As they travel, they interact with gas and magnetic fields, slowly losing energy. Their presence affects the physical state of interstellar space. Supernovae play a critical role in the galaxy's evolution. When massive stars end their lives, they release enormous amounts of energy. This energy heats surrounding gas, drives shock waves, and spreads newly formed elements. Over time, supernovae help regulate how quickly new stars can form. The rate at which the Milky Way forms new stars is moderate. It is neither a starburst galaxy nor a dormant one. Instead, it produces stars at a steady pace, converting gas into stars gradually. This balance has allowed the galaxy to remain active for billions of years. Gas does not remain permanently locked in stars. As stars age, they lose material through winds or gentle shedding. This returned gas mixes back into the interstellar medium. The cycle of star formation and stellar death continues, slowly reshaping the galaxy. The Milky Way is not isolated in space. It belongs to a small collection of galaxies called the local group. This group contains a few large galaxies and many smaller ones. All are bound together by gravity and move through space as a loose family. The Andromeda Galaxy is the largest member of the local group besides the Milky Way. It is another spiral galaxy, similar in structure but somewhat larger. Measurements of motion show that Andromeda and the Milky Way are moving toward each other. Their future interaction is inevitable, though still far away. When large galaxies merge, the process unfolds slowly. Their disks may distort, and their spiral patterns may fade. Over time, the combined system can settle into a new shape. Such mergers are a normal part of galactic evolution across the universe. Despite these long-term changes, the Milky Way appears stable on human timescales. Its large-scale structure changes so slowly that it seems permanent from one generation to the next. The night sky looks much the same as it did thousands of years ago. Only careful measurements reveal the motion beneath the stillness. Studying the Milky Way presents unique challenges because we are inside it. We cannot step back to see it whole. Instead, astronomers rely on indirect methods, mapping the galaxy piece by piece. Patterns emerge gradually as data accumulates. One important tool for mapping the galaxy involves measuring stellar distances. Astronomers use several techniques, each suited to different ranges. By combining these methods, they build a three-dimensional picture of the Milky Way's structure. This work is ongoing and constantly refined. The disk of the Milky Way contains both a thin and a thick component. The thin disk holds most of the gas and young stars. The thick disk contains older stars that extend farther above and below the galactic plane. These two components reflect different stages in the galaxy's past. Stars in the disk do not move in perfectly flat paths. They oscillate gently up and down as they orbit the center. These motions can be influenced by past interactions and internal dynamics. Over time, the disk maintains its overall shape despite this constant motion. Beyond the disk lies the extended halo, which reaches far into space. Its stars are sparse and many follow highly elongated orbits. Dark matter dominates this region, shaping the galaxy's gravitational field. The halo's true extent is difficult to define precisely. Some halo stars move in directions opposite to the disk's rotation. This unusual motion supports the idea that they originated outside the Milky Way. Their paths preserve evidence of ancient mergers. Each such star carries a fragment of galactic history. Neutral hydrogen gas fills much of the galaxy's outer regions. This gas emits radio waves at a specific wavelength that can pass through dust. By observing this emission, astronomers can trace the structure of the Milky Way even where stars are hidden. These maps reveal the warped and extended nature of the disk. Above and below the galactic center, large bubbles of hot gas have been detected. These structures suggest energetic events in the past. One possibility is that the central black hole experienced periods of higher activity. Another is that clustered supernovae drove gas outward. The spiral arms of the Milky Way are not all the same. Some are more prominent, while others are weaker and less defined. Their shapes can change over time as material moves through the disk. Spiral structure is dynamic rather than fixed. Within certain regions of the galaxy, star formation occurs in large complexes. These areas can give rise to many massive stars at once. The radiation from these stars shapes nearby gas and dust. Over time, they carve cavities and trigger further star formation. Massive stars live fast and end quickly. They burn through their nuclear fuel in a few million years. When they explode as supernovae, they leave behind compact remnants like neutron stars or black holes. These remnants continue to influence their surroundings. Neutron stars are extremely dense objects formed from collapsed stellar cores. Some emit regular pulses of radio waves and are known as pulsars. By studying pulsars in the Milky Way, astronomers test theories of gravity and dense matter. These objects act like precise cosmic clocks. The Sun is considered an average star within the Milky Way. It is not especially massive or unusually bright. Its relatively stable output has allowed life on Earth to develop. In galactic terms, the Sun is a common type of star. Observations over recent decades suggest that planets are common around stars. Many stars in the Milky Way likely host planetary systems. These systems vary widely in structure and composition. Planet formation appears to be a natural outcome of star formation. The idea of a galactic habitable zone has been proposed to describe regions where conditions may favor long-term stability. Such zones would balance element availability with lower exposure to energetic events. This concept remains an area of ongoing research rather than a settled conclusion. Gas clouds within the galaxy can stretch and deform under tidal forces. These forces arise when gravity acts unevenly across extended structures. Over time, tidal interactions shape spiral arms and streams. The galaxy's appearance reflects these subtle influences. Open clusters are looser groups of stars that form together in the disk. They contain fewer stars than globular clusters and are less tightly bound. Over time, gravitational interactions disperse their members. Many stars in the disk began their lives this way. The Sun itself likely formed in an open cluster. That cluster has since dispersed, and its stars have drifted apart. Some of the Sun's original siblings may still exist elsewhere in the galaxy. Identifying them is a challenging task. Radio emissions from the Milky Way reveal energetic processes invisible to the eye. These signals trace interactions between particles and magnetic fields. They help map regions of activity near the center and along spiral arms. Each wavelength adds another layer of understanding. Dust lanes follow the spiral pattern of the disk. They mark regions where gas and dust are concentrated. These lanes often coincide with star-forming regions. Their shapes help outline the galaxy's structure. From Earth, the Milky Way appears edge-on. This viewpoint emphasizes its band-like appearance. If seen from far outside, it would look like a flattened spiral disk. Perspective shapes how we experience our galaxy. As Earth orbits the Sun, different portions of the Milky Way become visible at night. Over the course of a year, the view slowly shifts. This seasonal change connects human cycles to galactic structure. The galaxy remains constant while our vantage point moves. In places free from artificial light, the Milky Way appears richly detailed. Countless stars and dark lanes become visible. Such views resemble how the sky looked to most of humanity for much of history. They offer a direct connection to the galaxy we inhabit. The Milky Way continues to evolve quietly. Gas flows, stars age, and small galaxies interact with it. These processes unfold over immense timescales. The galaxy's present form is just one moment in a long story still being written. Every atom in the human body was formed somewhere within the Milky Way. Many originated in stars that lived and died long before the Sun existed. In this sense, the galaxy's history is written into matter itself. We are physically connected to its past. Though vast, the Milky Way is only one galaxy among many. It is not especially unusual when viewed on cosmic scales, yet it is the only galaxy we can study from within in such intimate detail. This perspective gives us a unique understanding of galactic life. As the Milky Way rotates, it carries all its stars along in a shared motion. This movement is steady and unhurried. Night after night, the sky appears calm, even though everything is in motion. The galaxy remains quietly turning, whether observed or not. The Milky Way's rotation is not perfectly smooth. Subtle ripples move through the disk caused by gravitational interactions with satellite galaxies and internal structures like the central bar. These ripples gently shift stellar orbits over time. They do not disrupt the galaxy, but they leave measurable patterns that astronomers can detect. The disk of the Milky Way is slightly warped rather than perfectly flat. In its outer regions, the disk bends upward on one side and downward on the other. This warp is likely caused by gravitational interactions with nearby galaxies. and the surrounding dark matter halo. Such distortions are common among spiral galaxies. Gas in the Milky Way does not follow exactly the same paths as stars. Because gas can collide and lose energy, it gradually settles into thinner structures. Over time, this behavior concentrates gas toward the galactic plane. This concentration supports ongoing star formation in the disk. Some regions of interstellar gas are heated to extremely high temperatures. These hot regions are often created by multiple supernova explosions occurring close together. The combined energy forms large cavities filled with thin, hot plasma. These cavities can persist for millions of years before cooling. The Milky Way contains many supernova remnants, expanding shells of gas left behind after stellar explosions. These remnants interact with surrounding material, compressing nearby gas clouds. In some cases, this compression can trigger new star formation. In others, it can disperse gas and slow star birth. Stellar winds from massive stars also shape the interstellar medium. These winds push material outward over long periods, carving bubbles into surrounding gas. Even before a star explodes, it influences its environment. The combined effect of winds and supernovae continuously reshapes the galaxy's gas. The chemical composition of stars varies across the Milky Way. Stars closer to the galactic center generally contain higher amounts of heavy elements. This pattern reflects a longer and more intense history of star formation near the center. Farther out, stars tend to be more chemically simple. This gradual change in composition across the disk is known as a metallicity gradient. It provides clues about how gas moved and formed stars over time. By measuring stellar chemistry, astronomers reconstruct aspects of the galaxy's growth. Each star carries a chemical fingerprint of its birthplace. Some stars move in nearly circular orbits around the galactic center. Others follow more elongated paths. These differences arise from the conditions present when the stars formed and from later gravitational interactions. Over time, stellar motions slowly mix the disk. The Milky Way contains populations of stars that share similar motions and compositions. These groups are sometimes remnants of ancient star clusters or merged systems. Identifying them helps trace past events in the galaxy's history. They are subtle patterns hidden within the broader stellar population. The galaxy's bar rotates at a different speed than the outer disk. This difference creates regions where stars and gas experience resonances. At these locations, orbits can become more crowded or more sparse. Such resonances influence the distribution of matter in the inner galaxy. Gas flowing along the bar can be funneled toward the central regions. This process helps supply material to the inner disk and bulge. Over long periods, it may also feed the central black hole. The bar acts as a slow conveyor belt of matter. The Milky Way's central molecular zone contains dense concentrations of gas. This region is unusually turbulent compared to the rest of the disk. Star formation there follows different rules than in quieter regions. The reasons for this difference are still being investigated. Although the central black hole is currently quiet, evidence suggests it was more active in the past. Structures observed above and below the galactic plane hint at past outbursts. These events would have released energy into the surrounding gas. Their effects can still be traced today. Stars near the galactic center experience strong tidal forces. These forces stretch stellar orbits and can disrupt loosely bound systems. As a result, star clusters near the center tend to dissolve more quickly. Only the most tightly bound clusters can survive there for long. The Milky Way contains numerous stellar remnants beyond neutron stars. White dwarfs, the dense cores of low-mass stars, are common throughout the disk. Though faint, they contribute significantly to the galaxy's total mass. They represent the future state of many existing stars. Binary star systems are widespread in the Milky Way. Many stars form with companions, orbiting a shared center of mass. Interactions within these systems can alter stellar evolution. In some cases, they lead to dramatic events, such as novae. When material flows from one star to another in a binary system, energy can be released suddenly. These events can briefly increase the system's brightness. Though localized, they add to the dynamic behavior of the galaxy. Such interactions are part of everyday galactic life. The Milky Way hosts many variable stars whose brightness changes over time. Some pulsate regularly, expanding and contracting in a steady rhythm. These stars are especially useful for measuring distances. Their predictable behavior acts as a natural measuring tool. Dust in the galaxy does more than block light. It also helps cool gas clouds by emitting infrared radiation. This cooling allows clouds to collapse more easily under gravity. In this way, dust supports the formation of new stars. The shapes of interstellar clouds are often irregular and filamentary. Turbulence, magnetic fields, and gravity all contribute to these forms. These structures can stretch across many light years. Within them, star formation occurs unevenly. The Milky Way's magnetic field follows the spiral structure of the disk. It is not uniform but twisted and folded. This field influences how charged particles move through space. It also affects the alignment of dust grains. Observations of polarized light reveal information about magnetic fields. As light passes through aligned dust grains, its properties change slightly. By studying this effect, astronomers map the galaxy's magnetic structure. These maps add another layer to our understanding. Cosmic rays interact with interstellar gas to produce gamma rays. Observations of this radiation reveal regions of particle acceleration. These high-energy processes occur throughout the galaxy. They highlight environments where energy is being redistributed. The Milky Way's outer disk contains fewer stars than its inner regions. Star formation declines with distance from the center. Gas becomes more diffuse and colder. This gradual thinning shapes the galaxy's overall appearance. Beyond the visible disk, faint stellar structures extend outward. These include streams and clouds left behind by disrupted systems. Though subtle, they are detectable with careful surveys. The halo contains very old stars with low metal content. These stars formed early before many cycles of enrichment occurred. Their properties offer insight into the early universe. Studying them helps constrain models of galaxy formation. Some of the Milky Way's smallest companion galaxies orbit deep within its halo. These satellites are often irregular in shape. Many have lost gas due to the Milky Way's gravitational influence. Their evolution is shaped by this interaction. Tidal forces from the Milky Way can strip stars from satellite galaxies. Over time, this process creates elongated streams. These streams follow the original orbit of the satellite. They act as sensitive tracers of the galaxy's gravitational field. The distribution of dark matter affects how these streams evolve. By modeling their shapes, astronomers infer properties of the dark matter halo. This method provides indirect information about matter that cannot be seen. It links visible stars to invisible mass. The Milky Way's disk contains both orderly rotation and random motion. While most stars follow the general rotation, each also has small deviations. These deviations increase over time due to interactions. The disk gradually becomes dynamically warmer. Despite this warming, the disk remains coherent. Gravity maintains its overall structure. Even after billions of years, the Milky Way retains its recognizable form. Stability and change coexist within it. Interstellar gas clouds can collide gently as they orbit the galaxy. These collisions compress gas and alter cloud shapes. They do not resemble violent crashes, but slow interactions. Over time, they influence where stars form. Some regions of gas emit strongly at specific wavelengths. These emissions arise from atoms and molecules transitioning between energy states. By studying these signals, astronomers identify the composition and conditions of interstellar material. Each emission line carries physical information. The Milky Way contains large-scale patterns in gas motion. These flows respond to the galaxy's gravitational potential. They can feed spiral arms or move material inward. Such flows are part of the galaxy's long-term balance. The Sun's orbit around the galactic center is not perfectly circular. It moves slightly closer and farther from the center over time. These variations are small but measurable. They reflect the complex gravitational environment of the disk. As the Sun travels, it passes through different interstellar environments. The density of surrounding gas changes slowly. Over millions of years, this can affect the size of the heliosphere. The solar system is not isolated from galactic conditions. Occasionally, nearby supernovae influence the local environment. Their shock waves can pass through surrounding space. Evidence suggests such events occurred near the Sun in the distant past. These influences are rare, but part of galactic life. The Milky Way's star formation history is not uniform. Periods of higher activity likely alternated with quieter times. These variations may be linked to interactions with satellite galaxies. The record of this history is encoded in stellar populations. Some stars in the disk show signs of having migrated from their birthplaces. Over time, interactions can change a star's orbital radius. This radial migration mixes stellar populations. It blurs the connection between age and location. The galaxy's ability to retain gas is influenced by its mass. The Milky Way is massive enough to hold on to much of its gas. This allows continued star formation. Smaller galaxies often lose gas more easily. Hot gas surrounds the Milky Way in an extended halo. This gas is difficult to observe directly. Its presence is inferred from absorption features in distant light. It represents a reservoir of material connected to the galaxy. This hot halo gas may slowly cool and fall toward the disk. If so, it could help sustain star formation over long periods. The balance between inflow and outflow shapes the galaxy's future. These processes operate quietly and gradually. The Milky Way's structure reflects a balance between gravity, motion, and energy. None of these forces acts alone. Together they maintain the galaxy's form while allowing slow change. This balance has persisted for billions of years. Stars near the Sun share similar velocities, forming local moving groups. These groups are not bound clusters but temporary associations. Their shared motion reflects past dynamical events. They provide insight into the disk's evolution. The Milky Way's luminous matter represents only a small fraction of its total mass. Most of its mass resides in dark matter. This unseen component shapes the galaxy's overall behavior. Its nature remains one of astronomy's central questions. The Milky Way also contains vast regions where star formation has nearly ceased. In these quieter zones, gas has become too diffuse or too warm to collapse efficiently. Stars there continue their long lives with little interruption from new stellar births. These calm regions contribute to the galaxy's overall balance between activity and rest. Some stars travel at unusually high speeds compared to their neighbors. These so-called runaway stars may have been ejected from clusters through gravitational interactions. Others may have received a powerful kick when a companion star exploded as a supernova. Their rapid motion carries them far from their birthplaces. A small number of stars move fast enough to eventually escape the Milky Way entirely. These hypervelocity stars are rare and intriguing. Their speeds suggest interactions with the central black hole or dense stellar regions. Once released, they travel alone through intergalactic space. The Milky Way contains many stellar associations that are only loosely bound. These groups share a common origin but disperse quickly. Over millions of years, their stars blend into the general disk population. Such associations illustrate how transient many stellar groupings are. The galaxy's gas disk extends farther outward than its stellar disk. Neutral hydrogen can be detected well beyond the visible stars. This extended gas reservoir traces the outer structure of the Milky Way. It also hints at how the galaxy interacts with its surroundings. The outer disk shows signs of ongoing accretion of material. Gas from the surrounding environment can slowly join the galaxy. This infall contributes fresh material for future star formation. It also subtly alters the disk's dynamics. The Milky Way is surrounded by a faint population of high-velocity gas clouds. These clouds move differently from the disk's rotation. Their origins are still debated, with some possibly falling in from outside the galaxy. Others may be recycled material expelled long ago. The galaxy's spiral pattern is influenced by both internal and external forces. Interactions with satellite galaxies can strengthen or distort spiral arms. Internal instabilities can also reshape them. The spiral structure reflects a balance of influences rather than a single cause. The thickness of the disk varies with radius. Closer to the center, stars are more tightly confined. Farther out, the disk becomes puffier and more diffuse. This variation provides clues about the galaxy's formation and heating processes. The Milky Way's bulge contains stars with a wide range of motions. Some rotate with the disk, while others move more randomly. This mixture suggests a complex formation history. The bulge may have grown through both internal evolution and mergers. Observations indicate that the bulge includes both old and intermediate age stars. This diversity implies that star formation there did not end early. Instead, it continued intermittently. The bulge is not a single-age structure. Some stars near the center follow boxy or peanut-shaped orbits. These shapes arise from the dynamics of the galactic bar. They contribute to the bulge's distinctive appearance. Such orbital structures are seen in other barred galaxies as well. The Milky Way's central regions emit strong infrared radiation. This emission comes from warm dust heated by nearby stars. Infrared observations reveal structures hidden in visible light. They provide a clearer view of the galaxy's inner architecture. Large surveys of stars have revealed subtle waves in stellar motions. These waves may result from past interactions with satellite galaxies. They propagate through the disk over long timescales. Their presence shows that the disk remembers past disturbances. The galaxy's stellar disk is composed of multiple overlapping populations. These populations differ in age, chemistry, and motion. Together they form a layered structure rather than a single uniform component. This complexity reflects a long history of change. Some stars show chemical signatures that differ from nearby stars. These differences can indicate formation in distinct environments. Chemical tagging helps identify stars that formed together long ago. It allows astronomers to reconstruct dissolved clusters. The Milky Way contains a large population of low-mass stars. These stars burn their fuel slowly and can live for trillions of years. Many formed early in the galaxy's history and are still shining today. They contribute significantly to the galaxy's longevity. Brown dwarfs also exist within the galaxy. These objects are too small to sustain hydrogen fusion. They emit very little light and are difficult to detect. Despite this, they may be numerous and contribute to the galaxy's mass budget. The galaxy's stellar population includes remnants of massive stars in the form of black holes. Most are isolated and invisible unless interacting with companions. Their presence is inferred through gravitational effects or high-energy emissions. They represent the endpoints of stellar evolution. Some black holes in the Milky Way are part of binary systems. When they accrete material from a companion, they can emit X-rays. These systems allow astronomers to study strong gravity. They provide insight into extreme physical conditions. The Milky Way's X-ray emission also arises from hot gas in supernova remnants. These regions glow as shock-heated material cools. X-ray observations trace the energetic side of the galaxy. They complement studies at other wavelengths. Gamma-ray observations reveal regions where particles are accelerated to extreme energies. These processes occur near supernova remnants and possibly near the galactic center. The resulting radiation highlights sites of intense activity. Such regions are relatively rare but significant. The galaxy's interstellar dust affects the color of starlight. Shorter wavelengths are scattered more strongly than longer ones. This causes distant stars to appear redder. Astronomers correct for this effect when measuring stellar properties. Extinction by dust varies across the sky. Some directions are heavily obscured while others are relatively clear. This uneven distribution shapes our view of the Milky Way. It influences which regions are easiest to study. The Milky Way's disk is tilted slightly relative to the halo. This misalignment may result from past interactions. It contributes to the disk's warp. Such features show that the galaxy is not perfectly symmetrical. The galaxy's gravitational potential is not uniform. Variations arise from spiral arms, the bar, and dark matter. These variations influence stellar orbits. Over time, they can redistribute stars within the disk. Stellar encounters within the disk are usually gentle. The vast distances between stars prevent frequent close passes. As a result, stellar systems remain stable for long periods. The galaxy evolves through collective effects rather than individual collisions. Occasionally, stars pass close enough to perturb planetary systems. Such encounters are rare in the disk. In dense clusters, they are more common. The environment influences planetary stability. The Milky Way's star clusters gradually dissolve. Tidal forces and internal interactions pull them apart. Their stars join the general field population. This process enriches the disk with stars of shared origins. The halo's globular clusters are more resistant to dissolution. Their dense structure allows them to survive for billions of years. Even so, some show signs of tidal stripping. Streams of stars can trail behind them. The Milky Way's gravitational influence extends far beyond its visible components. Satellite galaxies feel this pull and respond to it. Their orbits reveal the galaxy's mass distribution. Studying them refines models of the halo. Some satellite galaxies contain little gas. This gas loss may result from interactions with the Milky Way's halo. As satellites move through hot gas, their own gas can be stripped away. This process alters their evolution. The Milky Way's hot halo gas exerts pressure on infalling material. This interaction affects how gas accretes onto the disk. It can slow or redirect inflows. The halo acts as a buffer between the galaxy and intergalactic space. Observations suggest that the Milky Way's star formation rate has declined over time. Early in its history, star formation was likely more vigorous. As gas was consumed, the rate gradually decreased. This trend is common among spiral galaxies. The Milky Way's stellar disk exhibits a mix of circular and eccentric orbits. This diversity reflects the accumulation of dynamical heating over time. Older stars tend to have more varied motions. Younger stars follow more orderly paths. The Sun's motion relative to nearby stars includes small oscillations. These motions arise from gravitational interactions within the disk. Over long periods, the Sun's orbit slowly changes. Even so, it remains within a stable region. The local neighborhood around the Sun is part of a larger structure known as the local arm segment. This region contains star-forming clouds and young stars. Its properties are typical of disk environments. It provides a representative view of galactic life. The Milky Way's spiral pattern may not be permanent. Some models suggest spiral arms form and dissolve repeatedly. If so, the current pattern is temporary. The galaxy's appearance may change over long timescales. Different traces reveal different aspects of spiral structure. Young stars, gas, and dust highlight arms clearly. Older stars show a smoother distribution. Combining these views provides a more complete picture. The galaxy's central bar may also evolve over time. Its length and strength can change. These changes influence the inner disk. The bar's evolution is linked to the galaxy's overall dynamics. Large-scale simulations of galaxies like the Milky Way reproduce many observed features. These models include dark matter, gas, and stars. By comparing simulations to observations, astronomers test theories of galaxy formation. The Milky Way serves as a benchmark. The galaxy's age is estimated from the oldest stars it contains. These stars formed shortly after the universe itself began. Their ages place a lower limit on the Milky Way's formation time. The galaxy assembled early and evolved gradually. The Milky Way's history includes both smooth growth and sudden events. Periods of calm were interrupted by mergers and interactions. Each event left subtle traces. Together they shaped the galaxy we see today. The Milky Way's present structure reflects a balance achieved over billions of years. Gravity organizes matter while energy disperses it. This interplay creates enduring patterns. The galaxy remains coherent amid constant change. From within the disk, the galaxy appears immense and slow. Its processes operate on timescales far beyond human experience. This scale allows stability to emerge. The Milky Way continues its quiet rotation through space. Even as individual stars are born and die, the galaxy persists. Its overall form endures. New generations replace old ones. The cycle continues without urgency or pause. The Milky Way does not have a clear boundary. Its influence fades gradually into intergalactic space. Stars, gas, and dark matter become ever more sparse. The galaxy blends into its surroundings. This gradual fading reminds us that galaxies are not isolated islands. They exist within a larger cosmic web. The Milky Way interacts gently with its environment. These interactions shape its future. Within this vast system, every component plays a role. Stars, gas, dust, and dark matter all contribute. Their interactions sustain the galaxy's structure. Together they form the Milky Way as it is now. The Milky Way's outer regions are shaped not only by what happens inside the galaxy, but also by its slow interaction with intergalactic space. Gas at the outskirts can be influenced by the larger cosmic environment, including faint filaments of matter connecting galaxies. These interactions are subtle, but over billions of years they affect how material enters and leaves the galaxy. The Milky Way is not sealed off. It participates in a wider cosmic structure. Intergalactic space around the Milky Way is not completely empty. It contains very thin gas and dark matter that extend between galaxies. The Milky Way's gravity draws in some of this material over time. This slow accretion helps replenish gas that would otherwise be locked into stars. The process unfolds so gradually that it leaves no sharp signature. The local group itself is embedded in an even larger structure. Galaxies are arranged along filaments and sheets, separated by vast voids. The Milky Way's motion is influenced by the collective gravity of nearby galaxies. Its path through space reflects this larger-scale environment. The Milky Way moves relative to the cosmic microwave background, the faint radiation left over from the early universe. This motion can be measured precisely. It reveals that our galaxy is not stationary, but part of a broader cosmic flow. Even entire galaxy groups drift through space together. The orientation of the Milky Way is fixed only relative to its own internal structure. There is no absolute up or down in space. What we call the galactic plane is simply the plane defined by the disk of stars and gas. This plane serves as a useful reference for mapping the sky. Astronomers use a galactic coordinate system based on this plane. It allows positions of stars, clouds, and other objects to be described consistently. This system is centered on the Milky Way rather than Earth. It reflects how we organize our understanding from within the galaxy. The Milky Way's disk contains subtle asymmetries. One side may be slightly denser or more active than the other. These differences can arise from past interactions or internal instabilities. Over time, such imbalances can even out or shift elsewhere. Some regions of the disk show signs of past bursts of star formation. These bursts may have been triggered by passing satellite galaxies. Their influence compressed gas and encouraged stars to form. Long after the burst ended, the stars remain as evidence. The stellar halo contains stars that are among the most chemically simple in the galaxy. they lack many of the heavier elements produced later. This simplicity makes them valuable probes of early cosmic conditions. Their light carries information from a time when the galaxy was still young. The Milky Way's dark matter halo is thought to be roughly spherical or slightly elongated. Its shape influences the motion of stars and satellite galaxies. Determining this shape is difficult, but stellar streams provide clues. The invisible structure leaves visible imprints. The total mass of the Milky Way cannot be measured directly. Instead, it is inferred from how objects move under gravity. Estimates depend on assumptions and data quality. Even so, they consistently show that dark matter dominates the mass budget. Gas clouds within the galaxy are constantly changing shape. Turbulence stirs them, gravity pulls them inward, and radiation pushes them outward. These competing influences create complex structures. No cloud remains static for long. The coldest regions of the interstellar medium can reach temperatures just above absolute zero. In these conditions, atoms move very slowly. Such cold gas is especially prone to collapse. It represents the earliest stage of star formation. Some molecular clouds persist for tens of millions of years without forming stars. The reasons are still debated. Magnetic fields, turbulence, or external pressures may delay collapse. These quiet clouds show that star formation is not inevitable. When star formation does occur, it often happens in clusters. Stars form together from the same cloud. Their shared origin gives them similar ages and compositions. Over time, these clusters disperse. Young star clusters illuminate surrounding gas. Their radiation creates glowing nebulae. These nebulae mark regions where stars recently formed. They fade as the gas is dispersed. The Milky Way contains many such nebulae scattered along its spiral arms. Some are small and faint, while others span many light years. They serve as visible signposts of recent star birth. Each one represents a brief phase in the galaxy's life. As stars age, their luminosity and temperature change. These changes follow predictable patterns. By studying these patterns, astronomers estimate stellar ages. This allows reconstruction of the galaxy's star formation history. The Sun is roughly halfway through its stable lifetime. It formed long after the Milky Way itself. Its existence reflects a mature stage of the galaxy. Earlier eras looked very different. The chemical elements present in the solar system reflect the galaxy's history up to that point. They include contributions from many generations of stars. This mixture enabled the formation of rocky planets. It also allowed complex chemistry to arise. The Milky Way contains regions where radiation fields are intense. Near massive stars, ultraviolet light alters surrounding gas. This radiation can both trigger and suppress star formation. Its effects depend on distance and density. Far from these energetic regions, the interstellar medium remains calm. Gas drifts slowly, influenced mainly by gravity. These quiet zones dominate the galaxy by volume. They provide a background against which energetic events stand out. The galaxy's overall appearance has changed over time. Early on, it likely looked more chaotic. As matter settled into a disk, order increased. The present structure reflects billions of years of gradual organization. The bar at the center may have formed after the disk was already in place. Its emergence changed how stars and gas move in the inner galaxy. Bars can grow or weaken over time. The Milky Way's bar is part of its ongoing evolution. The central black hole's mass appears well matched to the surrounding stellar bulge. This relationship is seen in many galaxies. It suggests linked growth between black holes and galaxies. The exact nature of this link is still studied. Although the central black hole dominates its immediate surroundings, it has little direct effect on the rest of the galaxy. The Sun's orbit is unaffected by it. The galaxy's large-scale dynamics are governed by distributed mass. The black hole is influential, but localized. The Milky Way emits a faint glow even in directions away from the disk. This diffuse light comes from scattered stars and gas. It shows that the galaxy's influence extends beyond its brightest regions. Nothing ends abruptly. From Earth, our view of the Milky Way is shaped by atmosphere and location. Some wavelengths are absorbed before reaching the ground. Space-based observatories reveal aspects invisible from Earth. Together, these perspectives build a fuller picture. Modern surveys have mapped millions of stars in detail. Their positions, motions, and compositions are catalogued. This wealth of data allows precise models of galactic structure. The Milky Way is becoming one of the best understood galaxies. Even with this knowledge, many questions remain. The nature of dark matter is still unknown. The exact sequence of past mergers is still being refined. Uncertainty remains part of the story. These uncertainties do not weaken our understanding. Instead, they show that the galaxy is complex. Each new observation adds nuance. The Milky Way is understood as a living system rather than a solved puzzle. Long after the Sun has completed its life cycle, the galaxy will still exist. Other stars will take its place. The disk will continue to rotate. The slow rhythm will persist. Looking at the Milky Way from Earth connects present moments to deep time. The light reaching our eyes left its sources long ago. It carries history across space. Each glance spans thousands of years. Within the Milky Way, countless worlds may exist. Some may be barren, others complex. Their variety reflects the galaxy's diversity. The full extent of this diversity is still unknown. What is certain is that the Milky Way is a stable home on cosmic timescales. Its structure has allowed stars like the Sun to exist for billions of years. This stability makes long-term processes possible. It is a calm environment in a vast universe. The Milky Way is neither young nor old in absolute terms. It occupies a middle age in cosmic history. It has endured much and will endure more. Its story continues quietly. Everything within it follows simple physical rules. From these rules, complexity emerges. Stars form, evolve, and fade. Gas flows, cools, and gathers again. And as the night remains still here on Earth, the Milky Way continues its slow rotation through space, carrying its stars, its gas, and its history forward without pause, without urgency, simply existing. Good night.